Okay, let's go from 2D to 3D. This will all take place on the SimWise side. All right. And just a little bit of historical reference, the original name of SimWise was Working Model 3D. Both 3D and 2D were created together by a small company in San Mateo, California named Knowledge Revolution about 25 years ago, and I had the really great fortune to be a part of that company, that team. All right, so the tools were designed to work together, and that's kind of how it goes. All right, so I'm looking at files. These are all the SimWise files in this directory. Let's go to here. We got Working Model 2D, and let's choose our forklift. It's got one question for us. How much do you want to extrude into the third dimension? We choose 1.5 meters. That's going to kind of give us an orientation, which in a way is kind of funny and a little tricky to look at. And so I like to quickly go to View, and I go to, this is probably my preferred view, which is the isometric view. But all these views are kind of set up so that Z is up, and that's the convention. Most mechanical dynamics tools work with Z in that orientation. So anyways, we basically need to rotate that assembly to accommodate that. And so the way to do it is right mouse click, let's rigidly join all the parts. You'll see the ground is kind of lined up with the X. And that means that using right hand rule that we rotate the whole thing by typing in 90 degrees. And then we undo this rigidly join. It's kind of funny that one of the joints, the one that connects the rack attachment with the vehicle, doesn't come back joined. Kind of an easy fix. All the parts are kind of where they need to be, and so I'm going to do what we call join in place. All right. And with that, we kind of got everything in 3 dimensions. Things look pretty good. There'll be a few fixes I want to work on. All right, I'm going to begin by kind of looking at this. I'm going to hide that load, and you'll see the, in 2D, all we did was one fork. Well, and it made it really big. All right, and so we're going to reduce that. We're going to make it maybe about that big, which I would say at most is 0.2 meters. And now we just got to move it. All right. Now these green things, these are the joints that were formed in Working Model 2D, and we're going to have to fix a few of these things too. But also they're showing to be way too big, and so I want to go to Display, and instead of going with the automatic sizing, let's make them 0.1. Right, so they're not so obtrusive now. All right, so anyways, we still got kind of the issue here. I'll probably fix a lot of these names. I'm not sure I'll get to all of them in this video, but let's at least make this the right fork. Might even change that to the right fork well, but for right now, I'm just keep the name. And what I want to do is I want to move one of the attachment points, and that's the basic idea of all these joints. Is that they're in 2D, they're all single dots or points. In 3D, they're all little local XYZ coordinate systems. We might get a little bit more into them, but for right now, I just want to kind of move it properly. And so this is the one that's attached to the lift rack. And I know that I already set the Z dimension, so that everything extruded, let's see, 1.5. Anyways, I did a little bit of thinking about this, and I came up with the number 0.0 or 0.55. Right? So you can kind of see the frame got moved there. Notice here that the joint itself has been split, and that's because the 2 corner frames aren't, co-located anymore. Anyways, again, I'm going to do kind of simple fixes. We might get it a little bit more into, frames and local coordinate systems later, but for right now, let's go with the assemble option, which means it will move the fork to bring the 2 cords together, and there we go. All right, and so that looks pretty good. All right, and so now I want to put in the left fork. All right, and put a frame here, and that position is we're kind of getting for free. I should have done this on the previous one. So let's get here, back to, and I want to get that number. All right, and we'll remember 0.55. All right, so again, let's get it to the rack attachment. Oh, sorry, lift rack. All right. So let's Paste that in, and for symmetry, we'll make it 0.55. Okay, so that's pretty good. All right, and I want to copy this and paste it. I want to get a view of that end surface, and I want to add a coordinate frame on the end surface. Okay, this time then surface is in -1, so we get that for free. And the other two are easy because we want to put them in the center of the face. So I'll put those in at 0, 0, 0. Now orientation I would be a little bit clever about. All right. Oops. And so I want to select that and select that. So both frames are selected. And this time I want to set them in world coordinates. And basically I would just want to match the world coordinate systems. Now again, it's something you got a lot of free choice. We could orient them any way we want, but there's something, especially as you start making measurements, that your intuition works pretty well if you keep things aligned with the world, right? And with those now set in the same orientation, I'll create my rigid joint. I'll use the option of bring the two coordinate frames together perfectly, which means X's, Y's, and Z's for each are pointing in the same direction. And it simply moves the origins, and we bring essentially the second fork in. Now that worked out pretty well. This next part I might explain a little bit more as we proceed, but for right now I'm going to use two coordinate frames to really attach that load back to this. All right. I'm going to just put both of them on each fork separately, and I'm going to take that guy, hold the shift key down, select that one, and under properties, position. Now these are going to be positioning relative to the forks that they're each attached. I want them each to be 0. We'll keep that, we'll get it for free. It means that's going to be on the top surface. We'll make that 0. And again, I like this idea of the world position reference, and we'll do the orientations the same, which they already are. Okay, good. All right, and now these are not going to connect to each other, but they're going to connect to the load. All right, and so I'm going to keep the load. Again, it's got that name from Working Model 2D. I'm going to just call it load now. All right, but I'm going to create the joints with each of them separately. All right, and so I'm going to make this a rigid connection. Rigid, create. All right, let's zoom in a little bit. I struggle a little bit to find that pan icon. There it is. Okay, I won't zoom in anymore. And it comes over as a cube, right? And that's really important. It's a real good visual, iconic way of explaining its functionality. But we're going to do something I hope you'll find clever. I think it's a real good way to do this. We're going to make it a rotation about the x-axis. I don't know if you can see it, but that's kind of a green cylinder, and basically means it would allow that load to rotate with regard to, you know, that x-axis, right? And so let's go view. All right, let's do the same thing, or let's create the joint here. And what I'm really doing is I'm kind of constructing the idea of a simply supported beam, right? It means that if all I'm really asking this frame to do, you know, the joint that we're going to put here, is not allow it to rotate according to that revolute axis. Now, why would I do that? Well, it means that we can measure the loads associated with each. And as we put asymmetric loads, and as we go, you know, on trajectories of motion for the vehicle where it does turns, you know, that load will get distributed properly between the two. So that's all I'm going to do to explain it right now. Certainly if it's confusing, you know, post questions and I'll happily respond to it. So anyways, with those two selected, let's go motion. And again, I like this idea of creating a rigid joint because it kind of gives you a good starting point. And so again, let's get it maybe to there. All right. And actually, this is what I'm going to do this time. View, let's look at a wireframe, and you'll see all this really well this way. All right. And so that constraint's right there, and we're going to allow it to rotate about all axes. It will go from a cube to a sphere. And then I'm also going to allow it to slide in both the X and Y directions, right? And that means that the only constraint it really can impose is that, it cannot go up and down. That's the one that will counter the revolute joint. And between the two, we have a rigid joint. But a rigid joint that then calculates the forces associated with each fork properly, all right? All right, so the rest of this is a little bit, I think, basic, all right? And it's really, let's just get the wheels in place, all right? And so this is our front wheel, and it's basically way too wide. We're not the Flintstones here, so let's make it 0.1, all right? And this needs to now be pushed to the edge, and this is the driven one. That's why it's got a motor right there. And it's this base point connected to the vehicle, and it's pretty much what we did before, which is make Z equal to 0.55. All right, mouse click, join, and this will be an assemble option. Again, it moves the tires we need. All right, in this one, again, it's not the, hopefully I'm not showing my age by making Flintstone references, okay? But anyways, let's keep on going. So we'll do the same thing here. Basically 10 centimeters is the dimension, and here's the joint, and the coordinate that's attached to the vehicle, Z.55. Join, assemble. Okay, and now we just got to get two wheels on the other side. So I kind of like the idea of put the frames in first. So let me put one there. Mostly because my memory of the numbers is still pretty fresh, right? And -1 for that. Here's the number that, the hard number to remember, if I remember it, 0.65. So you'll see it kind of puts it on that lower edge right there. And again, we get the Z equals -0.75 for free, right? And so we're going to make basically a copy of this wheel. Control C, V. And I'll put a frame on it. Doesn't really matter where, so I'm going to put a kind of a weird arbitrary place just to make the point. And I'm going to zero, oops, it on all of them. Okay. Now that is a frame that I really don't care about anyway, so it's the anchor. I'm going to delete that. All right. That's basically saying where the center of the ground was, right? And again, you might think there's an advantage of having the Z lined up with the cylinder. I don't really worry too much about it, and I kind of, again, I like the idea of aligning with world because it will match my intuition when I start to make, load measurements with that. And I know that with both being assigned in world, they are both the same, and the bodies will not change direction as we create the joint, right? And let's see, we got one more left to do. We got the frame right there. This time the number is 0.58. That's the hard number to remember. This one's -1, and we'll go with that -0.75, which we get for free because we put it on the right. Now notice that even though it's clear, I can't click on that. I need to kind of peek under it to get selection on that wheel. Copy, paste. Zero, zero, zero. Code selector. Select both frames are selected at the same time. That's the right wording. Mutually selected, something like that. All right. So let's line them up with the world. Okay, and create the joint. Let's view it shaded. Let's zoom back. I think it all looks pretty good. You do a couple of things. I'm going to hit run and see where we stand. All right, you can kind of see it right there. And again, it's choosing y to be the negative y to be the gravity direction, and that's just again, coming over from the working model 2D file where there was no z. We'll just make it minus z here. Okay, and we'll get into this a little bit more, but for right now I'm going to just select all 4 wheels. So let's just select them right here. And then let's select the ground also, and I'll choose to collide. Let's hit run. And you'll see it kind of works. I'd still say it's running a lot slower than it did in working model 2D. And maybe just to kind of make my last point on this, right, is I'll remove that contact, so allow them all to penetrate, and then I'll just kind of fix this right there so the vehicle itself is fixed. You can see it's running faster. And in general, this kind of notion of modeling contact in 3D, it is a way harder problem. It's impressive that this does it as well as it does. It maintains kind of that knowledge of the shapes and where the surfaces are, and it automatically makes those calculations for you. But we'll see in the next video that I'm going to introduce kind of a shortcut. And you'll see that we hadn't gotten to it yet. We hadn't run it for 2 seconds yet. That actuator was even programmed with that same profile. Let's see, where is that? That was assigned to it in working model 2D. All right, so thanks for watching.